Recording started. Just a reminder, all the recordings from this class, I think we've gotten every session, possibly there was a stroke with one, they're all posted to YouTube, so you can go there and find them. They're on a playlist there, and the link to the playlist is on the Moodle site. So please be aware you can make use of that. Okay, so I asked you to watch some videos for today. Well, on what subject were those videos focusing? Messages was a big part of it. And messages, particularly in the context of what sort of structure? Networks. So where we have links over which those messages pass. Those links form a graph. They form an interconnected set of vertices and edges between those vertices, links between those vertices. And it's a network. Things flow across that graph. Messages were the dominant type of construct that flows across this graph. So we send a message from A to B to have some sort of passing of information or to represent some sort of contact that takes place, some sort of influence. Sometimes those contacts can be can represent things that are highly physical. Sometimes those contacts can be informational in the sense that a person sends a message to another person on their cell phone or what have you. What we had seen in the previous few lectures, a notable ability to create rich agents within agent-based modeling, we really had treated the agents as solitudes. They were in isolation from one another. They happened to be within the same space, but they didn't interact. And with messages, all that changes. So we have interacting agents. We have agents that interact through this means of messages. It's not the only means of interaction, but it's a predominant one. It's a very common one, particularly for agent-based modeling. So today's lecture, I wanted to discuss some aspects of these networks with a particular highlight on the role of heterogeneity in terms of the number of contacts and this construct of scale-free networks. Networks that match where the number of connections someone has matches a power law distribution. Fancy terms. We'll figure out what that means, but basically what it means, it has a certain invariance of scale. No matter how many connections you have, call it K, your chance of having 2 times K connections has the same ratio regardless of K. So in other words, if you have 2 connections and your likelihood of having 4 connections is the chance of having 4 connections is half the chance of having 2 connections. The chance of having 200 connections is half the chance of having 100 connections. So no matter what scale you're at, you have sort of a similar drop-off in terms of the likelihood of having 2K connections, no matter how big K is. That's a very interesting sort of network. It's interesting because it has some interesting theoretic properties, but it also is notable for being very common in nature. And there's a reason why, as we'll see. These sort of networks are produced they're generated by a process of preferential attachment. There's sort of a reinforcing feedback loop. Those who have many connections now are more likely to get new connections. Think about a website. If it already has a lot of connections to it, people are more likely to find it easily and link to it. Or in this day where it's rare, people perhaps go and rely purely on links, but rely on search engines like Google. If you're pretty far up in Google's list, people are more likely to come to your website, and you're even further up in Google's list. So there's these positive feedbacks that reward connections. You already have lots of connections, you're more likely to get more connections. So we'll take a look at scale-free networks, which are a dominant feature of or a notable feature of natural systems and of human systems. Whether it's in the structure of the internet, whether it's in the patterns of our social networks, we see these types of scale-free networks emerging again and again and again. And they have some very interesting and very sobering properties, particularly when it comes to factors involving contagion. So we'll be talking about this today. Broadly speaking, when we are considering networks, there's a variety of factors that come into play when talking about a network. One of them is the issue of heterogeneity. People differ in terms of the number of connections that they have. Some people have more connections, or some people have more contacts with others than others do. That's one big issue that comes in that we want to capture with networks. Another factor is the issue of locality. You may have contact with 5 people per day, but it makes all the world of difference in terms of, say, the spread of a communicable disease like Ebola. Whether you have those connections with the same 5 people every day, or with 5 totally different people from day to day with no continuity. If you're having with the same people day to day, say your nuclear family, say your best friends, say your workmates, your roommates and your partner, if it's the same set of people, there's locality in the network. There's persistence in the connections, and an infection may spread, but it will spread more locally. You may be sick, but you're exposing the same 5 other people to illness every day. Whereas if you're sick and exposing totally different people to illness every day, it turns out it can spread very quickly. It can be seeded across the network. So we're going to be talking about this. And one of the main reasons we're interested in that first property, heterogeneity, is because for activities involving contagion, it's very, very central to governing the dynamics. Often a small number of individuals with a large number of connections make all the difference. So if you look at, for example, in sexually transmitted infections, and you look at the relative frequency, here shown on a log graph, of having different numbers of connections, you'll find that most people, in terms of sexual connections, have rather few partnerships per year. But some people have lots and lots of partnerships, as in hundreds. And it turns out that it's kind of the tail wagging the dog. Those small numbers of individuals have a vastly disproportionate impact on the remainder, on how the infection evolves in the population. We can plot it on a log graph, and you'll see a very striking pattern here where if you plot out the number of connections they have, say, in a 1-year period on the x-axis, on a log fashion, and the y-axis, the relative frequency, number per 100,000 people or what have you, you get a straight line. And that's the characteristic of a scale-free network. And when we have this sort of construct, we see this very sharp drop-off. Many people have few connections. Small number of people have lots, but those small number may make much more of a difference in terms of how the infection evolves than the bulk of people with small numbers of connections. It's really those people with high number of connections that drive things. Why is that? Well, someone with a high number of partners is more likely to be infected by others. They're kind of magnets for infection. They're connected with lots of people. And if there's just 1 or 2 of those people out there to whom they're infected, or to whom they're connected, one of those 200 people with whom they have contact, they have a good chance of getting infected. So they're more likely to be infected by someone, and given infection, they're more likely to pass it on. They're more likely to spread it, because they have lots of people to whom they can disseminate it. Hundreds, potentially. So these people with large numbers of connections are at great risk of getting infected and of great influence if they are infected in passing it on. And all in all, they have a disproportionate footprint on how that infection spreads. And for this reason, back in the 1980s, people realized that if you're focusing on targeting interventions for things like sexually transmitted infection, much of the game is about this issue of finding those people who are in the core groups, these people who have a large number of connections and have this disproportionate impact. And if you could focus on them, it was recognized you can get great bang for the buck. You can make a real difference. If you could change the sexual behavior to safe sexual practices of one of those people compared to 100 people, outside of that group, you still might be doing better by focusing on that one person. The numbers will be different in different contexts, but the point is those people may have this greatly disproportionate impact. And conversely, we may see very different infection rates in these high contact rate individuals who shouldn't be sampling just people at random in the population. We need to be focusing some of our efforts on these individuals who are really at the center of things in terms of infecting others. So when we built classic SIR models, stood before you a few weeks ago talking about this stuff, we saw something like this. And the notation was a little bit different. Instead of y, does anyone recognize y here? What did we call y before? Okay, is it S? It's close. It's I. It's actually I. I, if the eyes have it. It was cap I. Yeah. How do we recognize that? Because, well, what does this first term represent? It's people getting infected, right? If this were S dot, there'd be a what in front of it? Minus sign, because people are leaving the susceptible state. Here they're coming into the affected state. So this is I dot, the rate of change of I, number of people per unit time by which it's changing. So that's this term, and the first term is the infection term, new infection. So what's the second term? Recovery. Or recovery. On average, they stay infected for D time. First order delay. Familiar construct. Okay. So here we had C, and I kind of glossed over it, but it's a mean contacts per unit time. And the idea was we'd kind of, look at people in the population, find the average contact rate, and say that's kind of representative of what's going on. It's the average contact rate. And we reasoned about beta, the chance for discordant contact of infection spread, and the fraction of the population that had it. So remember, 100 people per day on average, 50% maybe of which are infected. So 100 times 0.5 or 50 contacts per day with an infected person, each one conferring beta. That was the idea. But that goes out the window to a degree here, because for situations where you have large heterogeneity, you have some people with lots and lots of connections, but many people with very few. Talking about the typical case, the average person, or the average number of contacts per day across the population, is frankly going to be way off from what's really going on. We're not capturing this heterogeneity. We're not capturing that some of the people have a disproportionate risk associated with disproportionate impact, and some have very little. So this idea of just dealing with the typical person or the typical number of contacts, it turns out it has to go out the window. And I wish I had time to cover all of this, but the opportunity cost is too high. But if you focus down on this, you can actually reason about how this has to change to take into account the variability. And one of the ways we could do it is we could recognize that this population that we've been just treating as an undifferentiated mass of susceptibles or infected, you could break them up into groups according to the number of contacts they have. Some of these susceptibles have no contacts per unit time. Some have 1. Some have 2 per unit time, say per year. Some have 3. And we can break them up into those groups. And it turns out that if you do that, you can start to reason about the number of people who have, say, eye contacts per unit time. But you have to do it in a way that's subtle. So, for example, here we have people, for example, with eye contacts. We call the numbers of people x sub I. Each of those people has how many contacts per day? By definition, they have eye contacts per unit time. And they have contacts with others in the population. And what's the fraction of that population that's infective? Well, you might think, good, it's just the total number of infected people in the population divided by n. But it turns out that if you're having contacts with others in the population, you have eye contacts per year with somebody, maybe it's 10. Those contacts that you're having are not themselves evenly distributed among the other people in the population. Maybe 50% of the whole population is infected, but your contacts are preferentially will tend to be with those who also have large numbers of contacts. Not because, and I'm not even assuming here that you particularly like those people compared to others, it's just that if you look at all the contacts out there in the population, many of them are occurring according to by this group on the right here. There are contacts occurring for those on the left, but the number of contacts occurring with people with a large number of contacts is disproportionately large. And you have to take that into account. You can't just say, what's the total fraction of people in the population that are infective, which you would be if you summed up y sub j here in the numerator. This is just the total of all over all the y compartments divided by n, the total number of people in the population. You can't do that. Instead, you have to ask, okay, what fraction of all contacts of all the number, if you consider how many contacts in the population are made by infectives, that's what you want to look at. So you need to recognize that a very large fraction of the contacts out there are being made by people with large number of connections, and hence those that are infected. And so you actually have in the numerator j term. J being the number of contacts they have, y sub j being the number of people who have that many contacts per day. And this is over the sum, a total number of contacts across the entire population. I don't have time to go through this in details, and I won't hold you responsible for the details of it. Just be aware that there's several layers to this, because it's not merely that people who have large number of contacts are at risk directly because they have more contacts. That's part of it. But the other part of the issue is their contacts are predominantly with people, or many of them are with people who also have lots of contacts and therefore extra at risk. Okay, so when you really boil this down though, and again I'm going to have to go quickly over this, what you find is that the effective number of contacts per unit time in the population, if you look at a population out there, some people have more contacts, some people have fewer. Rather than just dealing with the mean, call it C, number of contacts per unit time, you actually have to think about the variability in the contacts. And previously, we were just treating it as being what I'm calling M here, the average number of contacts. But now, actually, there's this extra term that enters in, which is the variance in the contacts divided by M. So if there's no variance, if everyone has the same number C of contacts, same number M of contacts, then we have the old analysis we did before. But it turns out if there's variability in contacts, some people have lots of contacts, some people have little. The effective C, the effective contact rate out there. By effective, I mean it operates as if it's a contact rate, is M, the mean number of contacts people have in the population, plus the variance in the number of contacts they have per unit time divided by M. This variance drives things. The larger the variance is, the more gap there is between some people have lots, some people have little, the bigger the effective contact rate will be. Why? Because those contacts will tend to concentrate in, and the infection will tend to concentrate in those with lots of contacts. Okay? So this is kind of ratio the variance to the mean that actually becomes a really big issue. And it can take the M and make it the effective contact rate going from M to M plus sigma squared over M. In other words, the variance divided by the mean plus the variance divided by the mean can be much larger than just the mean. Okay? So this is a really big effect. This is not a small effect. It's a big effect. And we tried to cast it here in the traditional equations to communicate some of its impact. And this is a particularly big issue for these constructs of scale-free networks. Okay? Scale-free networks, of all the networks we're talking about, ladies and gentlemen, they the highest variability in terms of the number of contacts that people have, the number of connections they have. So I'm going to use some shorthand here for the number of contacts that people have. We're going to call it K. This is, say, connections per year. Think about the number of sexual connections they have per year, or the number of connections in terms of short-term exposure to the same air. You know, so close enough to get infected by someone sneezing. It could be connections of that sort. In fact, all this applies to computer networks, and the number of links that a given site has. That could be K. Whatever your notion of connection is, we can use it here. Let's call that number of links a given node has K. Okay. The idea here is the chance of having K partners here, probability, or the relative frequency of having K partners in a scale-free network is proportional to, it's just some constant, times K to the minus, and it's typically called gamma. Okay? So it drops off, and depending on what gamma is, it will drop off quicker or slower, but it will drop off. So if you look at K here on the x-axis, and we plot P of K here on the y-axis, it will, that was the most ill-formed K. There we go. It's going to drop off. And depending what it is, again, it will drop off in different ways. But often, it turns out for human systems, gamma here is between 2 and 3.5 for human sexual networks, for example. Here, we're going to have this drop off as K increases. But it doesn't drop off all that quickly. And what's more telling is that if we plot it on a log-log graph, let's take the log of both sides here. Can anyone give me, what do we see? So over here on the left-hand side, we have log of P of K, and that's proportional to what on the right-hand side? We're taking the log of both sides. What is it proportional to on the right-hand side? What's the log of K to the minus gamma? Okay. Minus gamma times log K, right? Okay. And ladies and gentlemen, now suppose we draw out a plot of log K on the x-axis and log of the probability. And you can think of this as the relative frequency. Per 100,000 people, how many of them? What do we see? If you have a formula like this where this guy, you could call it y is proportional to minus gamma times x. I'm just trying to not let you get distracted by here. What do you see as a plot on a log-log plot here? In other words, what would you see as a plot on this? It's a line. And its slope is? Minus gamma. It has some intercept too, and so on, typically associated with the constant proportionality. But that's the line. And ladies and gentlemen, That's exactly the line that we saw just a minute ago with this, right? These are for different subgroups in the population. This is the line overall. And we see this sort of situation pop up again and again and again. We see it in the structuring of object-oriented software code in terms of coupling of things. We see it in the number of connections of links on websites. You could see it again and again in human activity. These are related constructs. And we'll talk about why. There are certain processes that give rise to this sort of construct. Okay. Yeah, question?
I'm not sure if this is relevant to
Yeah.
this, but I'm just curious. How did you get that
Yeah.
P of K is proportional to P?
Okay. Okay, so that is that's an empirically observed relationship. In other words, we observe it in real systems, this relationship. It is a characteristic of these sorts of networks that this is a property that they hold. So it's a definition of these sorts of networks, but these sorts of networks are of particular interest because they are so common. We see them so often. And we find that empirically, sort of if we observe them, they tend to be well described by this relationship. This relationship is a relationship that is commonly called a power law relationship. Power law relationship. And there's other contexts where it will come up as well. So we see it in terms of the dimensional structure of things in the world, the scaling behavior of if you build like a small scale bridge, how does its sort of how do its characteristics relate to a full scale bridge? They'll scale in this same sort of way. So it's a very common feature of many systems, but in this case, it's a pattern that we'll see emerge when we have many types of empirical networks. So we see it in nature, and we know that it comes from certain types of processes of building up these networks that I'll be talking about. Okay, so this is the definition of how a scale-free network varies as you consider the number of connections, and it, on a practical level, what we're saying is, I don't want this to be too mysterious, but there's going to be a constant of integration up front, where you're going to have some constant A up front to k to the minus alpha, and you can derive what this is so that it sums to 1, and so it's a probability distribution. But this is a very common empirical observation on the relative frequency of things. So it's not so much that this is derived from something, it matches really well what we see in the world, and therefore it's been formalized, and but it also is generally characteristic of power law relationships we see in other areas. So it's an important it's an important type of probability distribution. I don't know if that's helpful. Okay. Maybe talk more after class about it. I'd be happy to do it, but it is important both empirically and in some terms of some of the theory. Okay. So you get this sort of behavior with the scaling. Log x versus log y, if you have this sort of relationship. Okay. Now, at an intuitive level, what does this term mean? And why do we call it a power law relationship? Or why do we call it scale-free? Well, let's consider the probability that that we have. Suppose we consider P of k, and now we want to consider the probability of having twice that number of connections. 2k. P of 2k, right? What is that proportional to, folks? So suppose k is 5, and we're considering the relative likelihood of having 10 connections. So we have a certain number of people with p equals 5 connections per year, and we're considering what's the frequency of having 10 connections per year. If I have this, so I consider p of 2k, just substituting on the right-hand side, what's that equal to? What is that proportional to?
2k to the power.
Okay, that's 2k to the minus gamma. And can anyone expand that?
To the power.
Sorry?
2 to the power of 2 to the power of
2 to the power of minus gamma times k to the minus gamma. Okay, that's good. So if I divide p of 2k, if I say, okay, what's the probability of having p of 2k compared to p of k, what do I get? That's for p of 2k. 2 to the minus gamma times k to the minus gamma, and I divide it by p of k, what do I get?
2 to the minus gamma.
Yeah, 2 to the minus gamma. Now, what's striking about that is what? Maybe it's not striking you. It's independent of what? K. It doesn't matter if you're talking about comparing the probability of having 1 connection versus 2, or probability of having 2 versus 4, or probability of having 1024 versus 2048. It's independent of scale. It's the same relationship. So you could put it this way. Compared to your chance of having k connections, your chance of having 2k connections is always the same amount smaller. It's always the same. It's always reduced by the same amount, no matter what k is. Okay. It looks the same at any scale. It's just multiplied by a constant here. So here we have this behavior that, regardless of scale, we see this sort of relationship. And by the way, we've seen relationship in this in data collected from students like yourselves here on campus. We see this sort of behavior over wide ranges in terms of the number of connections people have, the duration of connections up to a certain limit. It's actually quite striking and reaches out and grabs you. So, let's consider a particular gamma. If gamma is 2, suppose, the chance of having 2 connections, say, versus 4 connections, it's going to be a difference of 4 times in the sort of the frequency of seeing 4 connections versus 2 connections. So there's 4 times as many people with n connections as with 2n connections. I'm using n for k here. If you consider gamma equals 3, doubling k always divides p of k by 8. So if we have gamma equals 3, there's 8 times as many people with n connections as with 2n connections. So here we have gamma as a big factor in sort of how quickly this drops off. If gamma is smaller, it'll drop off more slowly, and if gamma is larger, it will drop off more quickly. Okay, these sort of power laws. Now, we see this in a number of cases, and for certain types of networks, like types of human networks, gamma is often within fairly defined ranges. Because said for human sexual networks is between 2 and 3.4, something like that they found worldwide. And what's notable here is that if we try to integrate up this, we can derive what the probability distribution function is. This is the constant proportionality up front, gamma minus 1. So, as I said, there's some constant out front, A. it's actually gamma minus 1 is the constant there. Now, going on here, okay. So when we have these sort of systems which exhibit these sort of properties, one of the things that's quite interesting is that the variance of this, you may recall earlier that we derived, and I'm looking for it here. Do you remember this term we derived here, the basic reproductive number, the effective C, the effective contact rate, I argued. When you have variability, it goes as M plus the variance in the number of contacts divided by M. M is the mean number of contacts people have, and sigma squared is the variance of those number of contacts they have. Okay? The deal here, folks, is that the variance of a scale-free network, we can derive from computing the variance and its classic properties. So here, folks, we're computing the second moment. We can derive what the variance is. It's the expected value of x squared minus the effective value of x, quantity squared. And if we compute that, we'll get that's the variance. It's a definite, it's one of the expressions for variance. And if we do that, we'll find that we get an expression like this here on the right-hand side. And the striking thing is, oh, wonderful. Okay, well, that's kind of striking, but it wasn't what I had in mind. Striking thing is that if we're considering gamma's possible ranges of gamma, this only converges. This only, thanks. This only is valid. This only is a valid integral if we have gamma greater than 3. For gamma less than 3, ladies and gentlemen, the variance of this system here is undefined. The variance of this probability distribution. It's a probability distribution here. We have p to the k proportional, say, to k to the minus 2.5. That's a probability distribution. It'll sum to 1 and so on. It's nice properties. But its variance is infinite. It's an infinite variance. And what that means, ladies and gentlemen, is that if you have a situation where gamma is small, if you have a scale-free network where gamma is small, and so it tends, the probability, the relative frequency of having a certain number of connections drops off too slow, you can have an extremely high effective contact rate as a result. In other words, if there's, when I say it drops off slowly with increasing k, what I mean is there's quite a few people who have large k. The slope of this line here will be less steep, and there'll be quite a large number of people with large numbers of connections. And when you see that, ladies and gentlemen, the effective contact rate can get extremely high. Those large people with large number of connections can dominate. And it goes from being a situation that's closer to an effective contact rate equal to the mean number of connections to an effective contact rate which is dominated by this variance term. And the affection can spread very quickly and stay present in the population long after you think it should have gone extinct if you were just dealing with the average contact rate across people. So with scale-free networks, one of the reasons that they're of concern is that we have this great variability. And in some human systems, we do have gamma less than 3. And what that means is that you can have an effective contact rate that is extraordinarily high. And the infection can spread much faster than you would think if you went around surveying people and finding how many people they came into contact with. Why? Because a small group of the population has lots and lots of contacts. And it's a big enough group, because gamma is not, it's not too large, it's less than 3. It's a big enough group that you really can have extraordinarily high effective contact rates. And in theory, if it's really described by, if you had an infinitely large human population described by a scale-free network distribution, the effective contact would be arbitrarily high. It would be arbitrarily large. Now, obviously, it breaks down at a certain point. There's ranges over which it applies. The human population is only so large, and there's only such a range of P of X where you're really getting a single person with that number of contacts. But the fact that you see such variability in human systems does mean, in very practical terms, that the game changes fundamentally from your average case. You don't look at the typical person. You don't look like at the typical number of contacts they have per day. You need to look at the tail that wags the dog, the people with a large number of contacts. That is where the game is at. And if you're not on top of that, you're going to be spinning your tires, dealing with very low opportunity issues, very low leverage issues, when really you could be making a much larger difference by focusing on these individuals with large numbers of connections. These individuals who are out here on the right-hand side with large number of connections per year and who dominate the dynamics. Okay? So I know I went through that quick, but I want you to absorb the essential messages there and realize that heterogeneity matters. It matters because the people with large numbers of connections are simultaneously more likely to get infected and, given infection, are more likely to pass it on. Those are two independent things by which they're both really important. And moreover, if you have this sort of variability within a system, the effective contact rate is shaped not just by the average, but by the variability. And the variability can dominate for systems where the variance is very large. Those are important takeaways from this. With scale-free networks, the variability can be very large, particularly when gamma is small. And gamma is small, that is less than 3, for a lot of human constructs, for some important human constructs, including social and sexual mixing networks. So this is of considerable concern because it changes the game. It means we can't deal with averages for the population. We have to deal with these subgroups. A little bit more about these networks and where they come from before we go on to some experimentation. We're going to be building up some code. So where do these networks come from? Well, it turns out scale-free networks can be produced readily. In fact, the algorithm for generating them, if you go back and look at Barabazi and Reza Albert's paper from a few decades ago, it's a process of preferential attachment. There's a reinforcing feedback. You attach new connections as you introduce them into the network to the people who already have connections. If you already have connections, you're more likely to be given a new connection than if you don't have many connections already. So again, think about a site that has lots of visitors on Google, or that Google knows has lots of visitors, is more likely to be listed further up there in the Google listings, is more likely to be visited again. A site that has lots of connections from other sites is more likely to get up there in the Google listings. People are more likely to discover it and get more links to it from other sites. Often, people who have lots and lots of connections, be they collegial connections, working with people, or other types of mixing, they're more likely to discover others and to have connections with them. They're more likely to be known and to have people seek them out because of that, etc. So there's a reinforcing feedback here. The more connections you have, the quicker you accumulate new ones. And there's plenty of examples like this in the human world and outside. So these sort of processes of building networks, of adding connections where connections are already present, are a notable feature of a lot of systems. And when we do that, when we add connections in that fashion, what do we get? We get scale-free networks. Scale-free networks come out of it. Those are the generating processes for these sort of networks. So it's no accident we see these patterns again and again and again in the human sphere and in certain natural spheres. It's the same underlying generating processes that give rise to them. And in our planning, in our choices, in our decision making, in our analysis of them, we need to take advantage of the fact that it's not the average that matters. It's not the typical case that matters. It's the case that has disproportionate impact up here in the tail that matters. Okay? So that was a little bit about scale-free networks. I'd like to work with you in the balance of the time to explore some networks on our own in any logic. Shall we do that? Ladies and gentlemen, prepare to compute. Okay. So I'm going to, just for simplicity here, I'm going to divide this